My name's Professor David Lary, and I'm here with a team from the University of Texas at Dallas in the Hansen Center for Space Sciences, and our group is called MINTS, which stands for Multi-Scale Intelligent, Interactive and Integrated Sensing. So what we try and do is comprehensive, holistic sensing of the environment from micro scales to the global scale, using a whole array of sentinels, from satellites, robotic vehicles. We have sensors across cities recording 24/7. So we try and comprehensively characterize the environment. Today our exercise was to demonstrate an autonomous robot system that can rapidly, much quicker than the existing systems that we know of, to gather data, to then use machine learning to provide comprehensive maps of an environment that maybe you've never seen before. The aerial robot was carrying underneath it both a hyperspectral camera measuring these 462 wavelengths. It also had a thermal camera. The thermal camera can be useful for a whole range of things, and also a visible camera. So we had pre-programmed with our autonomous control software exactly the area we wanted the vehicle to survey. And in fact, in just over 3 minutes, it surveyed that entire area, and it took off automatically, it flew automatically, and it can also land automatically. And while it was flying, it was capturing this hyperspectral imagery, the thermal imagery, and the regular visible imagery. You can think of the robotic boat as giving us the ground truth. So we can rapidly survey a large area with the aerial vehicle and capture imagery, but we really need to know, what does that imagery correspond to? What do those spectra actually mean? So the boat was laden with a set of sensors, about 30 sensors in fact, a whole array, a sonar giving us the depth and the bottom type, the type of vegetation growth, and then a whole set of composition sensors, things like algae, oils, and we can also have a mass spectrometer that can measure all the components of the water and the air. So the boat goes out and directly sails underneath where the aerial vehicle was flying. So that precisely coordinated element is critical, because that allows us to rapidly get the relevant coincidences. Step one was we did our training of the whole wide area. We used our machine learning to learn the mapping from what's in the water to what the aerial vehicle sees. Then to exercise that team to check that it really works, we then release a known contaminant. We then fly over with the aerial vehicle. Do we actually see it? Can we map it? Yes, we can see it. Yes, we can map it. Then we send out our boat to the location of the contaminant to verify, okay, yes, we really did see it. This is how much we measure. And we not only were taking the real-time measurements, we were also doing underwater video of that over water for part of the verification. In our survey, which took about 15 minutes, we gathered close to 4,000 data points, completely autonomously. So you could see that you can have a very rapid collection. Once you've done that data collection, machine learning can create a map from what the aerial camera sees, and then create a map over a large area.